So it is our pleasure to have today Galyna Livshyts from Georgia Tech, who is also currently in Bonn, who will be talking to us about inequality related to the Log-Brunn-Minkowski conjecture. And also just a piece of information, she has shared a link in the chat where you can follow what she will be writing on the screen if you click on that.
Thank you very much, and thanks for inviting and letting me speak. I'll wave and I will switch off the camera now and I will go to the Scribble. So do you see the Scribble here? And again, let me point out that you can also join the link that is in the chat. And maybe if somebody posts kind of the link for those who join later, you can join later as well. Yeah, so I will just talk on some neat inequality. I'm just planning, hopefully not a very fast talk, I'm gonna tell you about some interesting facts that we stumbled upon, and I will explain the proof, and then I will dwell a bit more on it, and then I will explain why it kind of fell from the skies, and like where does it come from and why would we think of it. This is joined with Sasha Kolesnikov. Let me mention just very briefly a little bit of notation, and then I will introduce a bit more as I go. So a convex set K in Rn is a set such that for any pair of points and for any number between 0 and 1, we have this convex combination in the set, right? So it's convex set. I will denote volume in Rn by 2 sticks like this. Sometimes I will add an index, maybe to indicate the dimension. If I have a convex set K, let me just say that it is symmetric if whenever I have a point in K, minus X is also in K. So if X is in K, minus X necessarily has to be in K, right? So it's an origin symmetric set. I shall denote outer unit normal by nx, n with subindex x. So it's outer unit normal that is sticking out of the point x. It's a vector of length 1 that's orthogonal to the boundary of K, and it's pointing out, and yeah, it's at the point x. Let me remind you also the notion of the support function of the convex body K. Body usually is used in the sense that it's compact and has a non-empty interior. I shall consider also sets with empty interior, actually, either way. So the support function of a convex set K, let me say for point u, maybe it's denoted to be the maximum of x comma u, where x ranges in K. So in other words, the support function at the point nx, so let me try and draw it here, hx evaluated at the point nx is the biggest possible scalar product of x of all the points in K with this vector nx, and the biggest one happens to be when our vector is precisely vector x. Here maybe I should put y here, just so that I don't confuse you, right? So we look maximum y, best one is this one, x, and the scalar product is projection of x onto an x, so it's like this length. So hk and x is nothing but scalar product of x with nx. It's a distance from the origin to the hyperplane that's orthogonal to this vector. So this is all I wanted to say in terms of notation and preliminaries. Are there any questions so far about this? So it's pretty important to kind of understand the geometric meaning of this guy and kind of remember this picture. I'm gonna scroll down. If you want to scroll up again, you can always click the link that I posted in the chat to this scribble, and the scribble you can open in your browser, and you can always scroll up and see what I wrote before. So it's a cool thing to join if you want. Okay, so if there is no question, let me just start by stating a theorem, the first theorem. Actually. And like I said, my plan is to state it, to prove it, and then to explain, like, what the hell. Okay, so the theorem is like this: for any semi-norm on Rn, for any semi-norm, I shall denote like this on Rn, and any symmetric convex body. In this case, I do mean convex body bounded on an empty interior, K in Rn. We have the following weird inequality. If I integrate over the boundary of K, the norm of the normal vector squared divided by x and x, which remember was the support function. And if I integrate with respect to the boundary measure, so this is my whatever Hausdorff n-1 dimensional, just n-1 dimensional boundary measure, I can estimate this guy from above by 1 over the volume of K, again remember this is volume, times the integral of the norm of an x h minus 1 squared. And moreover, the equality, there is a lot of equality cases here. The equality is attained if and only if, firstly, the semi-norm has special form. If the semi-norm is nothing but the scalar product with some vector theta. Maybe let's say theta non-zero, because it's a bit boring if it's zero, right? And K is a cylinder sort of parallel to theta, in the sense that this is my K, this is my vector theta. I mean, here I have an n-1 dimensions, sort of. If my semi-norm is just the simplest possible one, just the length of the scalar product, then the equality is attained. So this is the statement that I shall prove. Are there any questions about it? Like I said, so far it's just the idea is that it's supposed to just fall from the sky.
Galyna?
And yes.
Even if it's a cylinder, only a linear functional is an extremisor, right?
Yes, exactly. Yes, yes. So this is the only situation. So these two things need to happen. Yeah. Yes. So this is the inequality again. If you forget it, you can always scroll up. I'll be kind of slowly scrolling down.
So
Yes?
So what's in the base of the cylinder? It's anything?
Absolutely anything, yeah.
Okay.
Any convex body set body. Yes.
So it's infinite cylinder? No, is it a product of the interval and any base?
So yes, okay, so yeah, let me write it in a cool way. So it's a product of minus theta times t or whatever, yes. Product with C, where C is an n-1 dimensional convex set. Bounded. Of course, everything, so like I said, K is a convex body. That's what I want to
Which
restrict
also needs
myself
to
on.
be symmetric, right?
Which is symmetric, yes. K is a symmetric convex body. So C is any, yes, symmetric convex set, symmetric convex n-1 dimensional, let me say body, but body in the sense that it's a body in n-1 dimensions.
Galyna,
Yes.
what if it's the semi-norm just Euclidean norm? Is it easier in this case, or?
So well, if it's Euclidean norm, I mean, okay. So if it's Euclidean norms, then nx is it's a unit normal.
Yes.
So you just have one. Now
Right.
on the right hand side you have the surface area. On the
Yes.
left hand side you have this guy. It's not easier, it's actually harder, but a little bit, not much. I can prove. So let me explain. It's actually okay. So it's not much easier than the general case.
Mhm.
But I'm planning to explain the proof. So
Okay.
it's a pretty easy proof. There is really like, I don't know, I don't think there is like all that much to it, but the cool thing is kind of, yeah, anyway, I'll explain everything. Any more questions about the theorem? But yes, it's not, so yeah, it's not easier. I would say it's not easier if it's Euclidean normal one, yeah. Let me make a remark that, so this inequality, let me call it star. Star can be equivalently written on the sphere. So I can just write, I can pass on the sphere instead of an x, I will write as a vector u. So u is a vector on the sphere. And instead of the Hausdorff measure on the boundary, I shall get so-called surface area measure of K on the sphere. So it's literally defined to be this way. It's a push forward under the, well, it's called the Gauss map when we associate a unit vector on the sphere with normal vector. So surface area measure of K. I can write it as integral of the sphere, so I shall have the semi-norm of u squared. At the bottom, as I already explained, I will have the support function evaluated at u. D, like I said, sk is appropriate whatever measure, surface area measure I have here, and it's bounded from above by 1 of the volume, and yeah, integral of norm of u, dsk of u, yep, squared. So this is I'm just rewriting it, and it's going to be convenient for me to use this notation. I hope it's okay. Any questions about this notation? Like I said, again, surface area measure is nothing but the push forward under this map of the Hausdorff boundary measure and my one-dimensional boundary measure. Okay. So I'm just literally just doing nothing. Let me note, by the way, that an x is defined uniquely almost everywhere. With respect to this surface area measure when set is convex, so this integration is it's understood in the almost everywhere sense very well. I don't need to talk about smoothness or anything. And without further ado, let me just prove the thing. So first of all, let me notice that in order to prove this inequality, it will be enough to show the following fact. So, okay, it is enough to show, I shall call it fact 1, for any fixed u on the sphere, the semi-norm for any semi-norm of u divided by the support function is bounded from above by 1 over the volume of k, integral over the sphere. I'm going to change the variable to w to make it a bit more clear. So I'm going to show this actually. And I'm claiming that it's enough to show this fact. Do you agree with me that it's enough to show this fact? If we, so this is our, let me call it double star, right? So if we have this fact 1,
We
we
have
immediately
square on the left, Galia. U norms.
yes, Dima. No,
No.
no. So indeed, let me outline. Yes, so if fact 1 is shown, then integral over the sphere of this u squared over hk of u, dsk of u, I can write it as the integral of the norm of u times the norm of u over hk of u, dsk of u over the sphere, yes? And then this cat I can pull out. So this guy, you see, I can just estimate as a number pointwise. Well, no, not this cat, just this cat, the specific cat. Yes, and well, it's smaller than 1 over absolute value of k, and then I will have the integral squared. Okay, it's like the slowest in history anyone has explained the sin, I guess. Yes, I hope I didn't bore you. Does it make sense? Yes? Dima? Yes?
Yes.
Okay, good. So let's agree that from now on, we will just be sure. And turns out that for this inequality, it's just enough to show this pointwise estimate, which is lucky. Okay, so let's try and show this pointwise estimate. Now, another reduction, the next reduction is, now what is a semi-norm? We're going to get rid of a semi-norm immediately. Recall that for any semi-norm, we can write a semi-norm of u as a supremum over all v in some set of u v by absolute value. This is just a definition of a semi-norm, pretty much, right? It's a dual representation. So in the case of a norm, you call it a dual norm, I guess, right? In the case of a semi-norm, there is also some sort of set where you can write it like this. Do you agree? Thus, in order to show what we want, yes, fact 1, it is enough to show what I shall call fact 2, which is for any vector u, for any vector v, and it's enough to restrict ourselves on the sphere. uv by absolute value over hk of u is bounded from above by 1 over absolute value of k, Sn minus 1. And here I shall have, just a moment, u v d sk of u squared. Yeah. Okay. No, not squared. Everything's squared. I freaked myself out for a moment. No, everything is okay. One thing I don't like Scribble for is that it doesn't have a small eraser. Okay. Indeed. Why is it enough? Well, if we have fact 2, right, then immediately we can put supremum on both sides. Right, and supremum over the some omega set smaller than or equal to k. I have supremum over omega and have this the thingy, and the supremum of integrals. You know, supremum of integral is always smaller than integral of a supremum for non-negative functions, right? So this is smaller than k integral, and then I will have supremum of the same thingy, t is k of u, and we will have fact 1 as soon as we have fact 2. So what I'm trying to say, it's enough to just have this, and it's enough to normalize ourselves on the sphere here because everything is homogeneous. Do you agree so far? I don't want to go too slow, but also I don't want to go too fast. Anyway, so if we prove this, we're in good shape. We proved everything. Okay, so here comes kind of the key point, several key points. Basically, how to estimate. This is kind of the main question in this business, which I haven't explained what it relates to, but how to estimate overall in general, in principle, 1 over the support function. Like what do we do with this? So here is a way to do that. Let us recall Fabinho's theorem. Fabinho's theorem. Nothing, no rocket science. Right, the volume of K can be written as an integral of its sections. Right, imagine here's our K. Here's some direction U, and we can write volume of K as an integral of the sections of K with hyperplanes orthogonal to U. Right, so here I use notation U perp plus TU to be the set of points of X and Rn such that X minus TU is presumably orthogonal to U, yes. So it's a hyperplane shifted from the origin by T orthogonal to U. This is my U perp plus TU. And I dissect K with these sections, yes. And I take n minus 1 dimensional volume of that thing and I integrate it and I get volume of K. Now question, where do I integrate? At some point, you know, if I take my hyperplane very far, I only get 0. So what are the limits of integration here? Can somebody tell me? It's 9 o'clock. I'm explaining things.
Support
Yes.
function, 1.2
Yes.
support function.
Yeah, thank you so much for that. Indeed, from minus the support function to the plus the support function we integrate, indeed, right? So support function is exactly, it's this shadow boundary to which we integrate that thing K. So thus, therefore, the volume of K can be estimated from above by 2 times the support function times the maximum over T and R of K intersected with U perp plus TU. Now, okay, where is this maximum achieved for a symmetric convex set? If we have a symmetric convex set, we consider a bunch of sections of a symmetric convex set. Which one is going to be the largest? For a symmetric convex, let me say body.
I think the one which passes through the origin.
Exactly. K minus TU is going to be maximized for T equal to 0. The one that passes through the origin is going to be the biggest one. It's a very classical fact in convexity. It's based on the fact that this function, this k plus blah blah blah, it's actually log concave. It's even 1 over n concave. But anyway, it's log concave in T because K is convex. It's a standard fact. It follows from Minkowski inequality, for instance. And if a function is log concave and symmetric, even, right, because the convex body is symmetric, it's going to have to attain its maximum at the origin. Right, so therefore, what do we have? I'm not counting on the convex geometry audience here, by the way, which is why I'm hoping to explain things. Yes. And therefore, finally, this is how we estimate 1 over hk, sorry, 1 over hk of u. It's smaller than 2 over the volume times the central section. Okay. So this little bit answers the question of how we estimate 1 over hk. Remember, our goal was to estimate the ratio of the scalar product and hk. So far, we figured out how to estimate 1 over hk. Any questions so far? Right, everyone agrees, hopefully. Hope I didn't lose like absolutely everyone. So yes, so far this is what we can do. Now, who can tell me what is written here? What is this? Note, I have here some kind of flat thingy, okay, intersected with u perp. It's something n minus 1 dimensional. And I'm multiplying this something n minus 1 dimensional by a scalar product of 2 unit vectors. So if I'm doing that, I'm actually doing nothing but projecting it on a hyperplane orthogonal to V. Right, so if this is, I don't know, if this is A, then this is A times UV. If this is orthogonal to U, this is orthogonal to V. I project a little flat piece. I just multiply by the cosine of the angle between them, which is scalar product. In other words, this is nothing but 2 over the volume times the projection of a section. N minus 1 dimensional volume of the projection of the section. Right? And now this thing I can actually estimate pretty easily. Well, I mean, I'm going to use a pretty rough estimate here. So a section, this K intersected with U perp, it's a subset of K. Therefore, I can always estimate the projection of a subset with the projection of the whole set. Right, and for this equality, I have this picture. And cool. And we're almost done. So what do we have so far? We have, well, we essentially, yes, done. We proved this. Yeah. Now, what did we want? What did we want? Let me scroll up. Let me know if you need me. Would you like me to kind of take a breath and slow down? Let me have a sip of water. Any question? So what did we want? We wanted this fact 2 over here, which was written like this, right? So let me rewrite it again. Fact 2, which we want. And so basically I'm gonna claim it's called Cauchy's projection formula. It claims that it's exactly the same. That the length of a projection is actually the area of the projection, sorry, is exactly this guy that's written here. Let me explain why this is the case, right? So do you agree that if I convince you that Cauchy projection formula is true, we were done with the proof of the theorem? Yes? Someone agrees? No?
Yes, Galyna.
Yes, thanks, Sparta. Okay, so yes, so how do we prove it? So there's a couple of pictures you can draw here. Let me draw one of them. So here is our K. Imagine that we draw the boundary as like kind of bunch of little flat pieces. Now, when I project my K onto hyperplane, I already told you that what happens with flat pieces, I multiply flat pieces by scalar products. So if this is my normal vector, this gets multiplied. So if normal vector equal to u, this gets multiplied by u times v. And each of those pieces gets multiplied by its own scalar product. And the area of each of those pieces is precisely this dsk of u, the surface area measure. That's what it stands for. And when I multiply each piece and put it down and multiply and put it down and multiply and put it down and add it all up, this is exactly the integral I have here. Except, of course, I have to multiply it by 1/2 because I do it on two sides. So I kind of cover two shadows if I do this procedure. So in order to cover one shadow, just multiply by 1/2. This explains Cauchy projection formula. In other words, those things are exactly the same, and we're done with the proof. That's it. Are there any questions so far? So of course I didn't explain why the hell we would even write this inequality down and think like, this should be true. But I'm going to. But so far, are there any questions? I didn't explain also the equality cases, but again, equality cases are here. Oftentimes it can be very hard, but here it's actually easy. Just follow the argument. We're not using any approximation here. We're not using anything. So just following the argument, we see that it's true only for cylinders because we have to have the equality in this Fabinho theorem. This gives you a cylinder, right? We have to have the equality when we do this projection of a section. Yeah, so that just gives you a cylinder. I mean, it's a bit more complicated than that, but like it's not, yeah, not very complicated. And any questions?
Galyna,
Yes.
I feel that in one place you just like put max supremum inside the integral. So
Yes.
I mean that there is a feeling that you can write inequalities of the same type, but more precise if you do such things.
No, excellent. So you're saying that there is a loss here that pains you.
Yes, something like that.
Well, okay, well, it pains me too. What can I say? But so there is something good here, that even in the case when the seminorm is precisely the scalar product, it does tell us something.
Mhm.
And if it's not, it also it tells us something. I'm going to explain in a moment what it tells us. But actually, following up Sasha's question, exactly here is a question. It looks like the thing is a bit, it's tight for cylinders, but maybe in some cases when it's not a cylinder, you can do much tighter. So if K is something specific, can we have a tighter bound? That's, well, that's at least one of the questions one could ask. And so for that, let me formulate another theorem. Well, actually, before I formulate another theorem, let me just say, first of all, how tight can the bound be? So it cannot be tighter. It cannot be tighter. The constant of this inequality cannot be tighter than 1/n. Indeed, if I take the right-hand side here, let me go back to the convex body notation. Maybe it's better. I can estimate it from below by integral of nx squared divided by the integral of x and x th. Do you agree? But this is just Holder, like Holder inequality. But I claim that this exactly just equals to 1/n of 1 over the volume th squared, since in fact volume of K can be written as 1/n of this integral. Why is this true? So this is like, let me just draw a picture for this formula. Imagine you have a polygon on the plane, and you want to calculate the area of the polygon. In order to do that, you sum up the areas of these little triangles here. In order to find the area of each triangle, you take here 1/2 times the altitude times the side, and you sort of sum them up. And here, integration replaces summation, 1/n replaces 1/2. The support function replaces this altitude of the latitude or altitude, I always forget, of the triangle, and this surface area measure replaces the side of the triangle. So long story short, I'm just saying the left-hand side in that inequality that I said is always bigger than 1/n times the right-hand side. So if you want a tighter constant, we cannot hope for it to be tighter than 1/n. But in fact, it turns out that it can be tighter in a lot of the cases, and it can even be very close to 1/n a lot of the time. So here is another estimate. Suppose, again, we have a semi-norm, and suppose K is some convex body, then we can always estimate again this right-hand side. From above, and here what I can put is 2 times the Poincare, I will explain in a moment, of Poincare constant of, in fact, let me say I can put the infimum over linear transformations. Volume preserving linear transformations. And here I can put 2 times the Poincare constant of tk divided by the in radius of tk and the left-hand side. Where, again, let me say so, r of tk is in radius, meaning it's a radius of the ball, largest ball contained inside tk. And the Poincare constant is the smallest number such that for any, let me just say, roughly speaking, admissible function, you have, let me just write average integral of squared minus average integral of f squared is smaller than or equal to c Poincare squared times the integral of the gradient squared. I'm not gonna really, tell all that much about it. It's kind of not directly the point of the talk. But the cool thing is that in some cases, this estimate gives a tighter bound. So in general, of course, I'm not gonna tap into this post-traumatic stress and talk about KLS and stuff, right? But because in general, of course, even if KLS is completely solved and it's still not going to give better than 1, like 1 is overall better, that we got in the previous theorem, constant 1. But in some cases, for some specific bodies, it's much better. So for example, for LP balls, so if K is the LP ball, PPN, which is the set of points x in a range such that the LP norm of x is smaller than 1, right? If K is an LP ball, then integral, then in this inequality, we can, for any semi-norm, in this inequality, we have this guy is bounded from above, and here I have some absolute constant times n to the power minus minimum 1/2 1 over p. So for LP balls, you see that we have something much better. So, well, I'm assuming that n kind of is big. So if the dimension is big, then we have something extremely small here for LP balls. For Euclidean ball, for example, we have 1 over square root of n. For cross polytopes, also we have 1 over square root of n. Actually, for cross polytop, one can get something of order 1 over n here. A very different argument, but in any case, so the point is that, yeah, in some cases we can get something much better. This result, any questions so far?
Galyna, for the Euclidean
Yes.
ball, 1 over square root n optimal?
For Euclidean ball, is it optimal? It's a good question. It's probably is. It's a good question. I think. Amazing question. Let me think. So I think it should be probably optimal. I think for the Euclidean ball, well, actually yes. Okay, it should. Yes, I think it should be optimal. Yes.
Okay.
Yes, I think it should be because of the proof. Because in the case of Euclidean balls, it's in radius. We don't lose anything. Yeah. Yeah. For the Euclidean ball, well, no, actually for the Euclidean ball, the support function is just constant. So we have just for the Euclidean ball, yeah, yes, for the Euclidean ball should be. It's just, yes, of course. No, for the Euclidean ball, it's just, we have just directly, yeah. 1 over the volume, I forgot here. You see, we have, yeah, just identity. But yes, so interesting question, I think very interesting question would be also about one ball, the cross polytop. But like I said, there is a way to do 1 over n, well, almost 1 over n. Any other questions?
Is it obvious that this Poincare constant divided by in radius is bounded by 1 over the volume of K? That this beats the previous bound?
It does not. What I'm saying, it does not. Previous bound here, no, volume of K exists here, but I made that typo. No, this guy is not gonna be in general overall. It's not gonna be smaller than 1.
I mean, I did not see volume of K. Okay, thank you, guys.
No, this is just our constant. Yes, thanks, Pato, for pointing out. I forgot to write the volume of K, of course. No, it's if the KLS conjecture is true, then it's absolute constant because the in radius is always bigger than 1. I mean, in some cases it's much bigger than 1, and you can ask if it's better to even instead of KLS estimating this ratio, for example. Grigorius once explained to me that it's not, but I mean, anyway, again, this is something that in my view is useful only for specific bodies, not in general. Any other questions so far? Cool. So let me explain. Actually, I don't have that much time. Let me recall mixed volumes just very quickly. The concept of mixed volumes, V with subindex K, where K ranges from 1 to n, of K and M, where K and M are convex bodies. So mixed volume is defined to be n minus K factorial over n factorial, K plus T M. And here I have K's derivative when T equals to 0. It's a definition of mixed volume. So we take Minkowski sum of two sets, take derivative, get the mixed volume. And so it's important to remember that mixed volumes of convex sets are always non-negative. Always for all K are non-negative. So two things why I want to use this remark. So first, I'm not going to prove the theorem. Let me just say that the theorem 2 is based on this pretty cool lemma. So I think it's pretty cool because it tells us something about like geometric measure theory using convexity, and I don't know how to get it without convexity. So I just want to tell you about the lemma. I think it's funny. So if K is, let's say, C2 smooth strictly convex body, in Rn, and let in this case just let it be a nice smooth norm instead of a semi-norm. It's just be a good guy, and fix a function u on K into R, be C2, maybe also W21, such that also continues up to the boundary, differentiables, okay, but let u just be a super nice function such that its normal derivative is a norm. Basically, that's what I'm saying. Fix some function of convex set such that its normal derivative is a norm. Then there is an estimate that we can have for this function. And the Hilbert-Schmidt norm of the Hessian of that function then can be bounded on average by the Laplacian integral of the Laplacian squared. And so this is something very specific to convexity. Hence, if we have a convex set K, at every point we stick a normal, right? We take a normal derivative of that function. Then it obeys this strange estimate. In principle, not every function obeys such an estimate, right? Laplacian is a trace, Hessian is the sum of squares of eigenvalues. So it's, if it could be that the trace of a matrix, is 0, but then this guy is non-negative. But in this particular case, if its normal derivative happens to be a semi-norm, then a norm, actually, yes, then we have this estimate. So why? Let me just explain it very briefly. The thing is that the Laplacian squared, we can integrate by parts, and if integrated by parts twice here, we get precisely just the Hessian squared plus some boundary terms. And the thing is that this boundary term can be estimated from above by a second mixed volume of K with a convex body M, where M is precisely, well, the support function of M is precisely that semi-norm that we have. And it's non-negative, like I said, mixed volumes are non-negative, and therefore we have this inequality. So it's kind of pretty funny. Anyway, and so because of this lemma, we use a lemma to prove the theorem because we just we've used this left-hand side as a normal derivative of some function, like I said, with some nice property, and we argue that for any data we can have a function with that property such that it's Laplacian equal to whatever we want, this right-hand side will be equal to the integral of the Laplacian, and so with some manipulations we pretty much do a bunch of manipulations and get that estimate. And I'm kind of out of time. So I didn't, and I ended up not explaining. But maybe if somebody asks where the legs grow from that inequality, I can briefly explain later on. But I will stop here. Thank you.
Thank you very much for the talk. Are there any questions?
So why do you need this inequality?
Yes, great, Father. So let me just very briefly explain that it relates to the Slogburn-Minkowski conjecture. So unfortunately, of course, I don't have any time to talk about it. So let me just say that there is this really, really cool conjecture by Borodsky, Lutlokian, and John, Log-Brunn-Minkowski conjecture, that together with Colisanti and Marsiglietti, we showed that it implies, so if this is a conjecture, so the conjecture implies that I cannot take credit, I'm gonna have to write something bad here, and then I will immediately write something good. Implies this inequality for any function f, and then later Eli Puterman, and actually even before him Chen Huang Li and Liu. I forgot to mention also Kolesnikov and Milman. They also generalized this application to something to so-called Log-Brunn-Minkowski, and they also did a lot with it. But these guys, they showed the reverse implication. They showed that this inequality for any function implies Log-Brunn-Minkowski, and Eli Puterman, in particular, he noticed a pretty cool thing that actually this guy, let me call it double star. Okay, so double star is equivalent to saying that for any k and m, as the second mixed volume of k and m, I have to put the coefficient here, n times n minus 1, plus the integral with the boundary of the norm associated with some polar here, x and x, is smaller than, and here I should put, and again, to be consistent with everything I'm saying, let me just say n squared over the volume of k. And I mean, one can do stuff with it in a variety of ways. So Log-Brunn-Minkowski is this very scary big conjecture, is equivalent to showing that for any pair of bodies, this inequality is true. And it has to do with certain just invariance properties of this local versions that we derived. The idea is that, and actually Kolesnikov and Milman, even they noticed that this invariance properties that, anyway, it doesn't matter. So the point is that this is the inequality that we want to show. And without this guy, it is something that's called Minkowski second inequality. Minkowski second inequality. So it is known. And what Sasha and I did, we said, okay, what happens without this guy? And we found that it is also true without this guy. That is our theorem 1. And
Galyna, when
yes,
you say without the guy, the coefficients in front stay the same, right? n minus 1 n square over the volume.
Yes, yes. So yeah, so actually there is no n squared here, just yeah, because yes. I mean, yes, there is n squared if you write it as a mixed volume. I'm avoiding this notation now, yes, but yes,
Okay.
yes. So the point is that without this first guy, this is our theorem. This is theorem 1, right? Without the second guy, it's just Minkowski's second inequality. The trick is to prove it together. And this is it's kind of not clear. It's true if the seminorm is specifically the interval, because in that case, the mixed volume will just be 0. Second mixed volume doesn't matter. Anyway, so this is kind of the point. So I think it's nice that we have at least some way to very sharply estimate the one over support function. So basically now the question is, can we adopt the ideas that I explained to do a bit more? So yeah, this I don't know. I answered Pad's question in a very long time. I'm so sorry for taking such a long time, but yeah. Let me put the camera.
Do you get something from that if K is a cylinder? Because then you have equality. That means, in that case, the mixed volume would be 0, right?
Yeah, so if we have equality here, the mixed volume will be 0, exactly. So in fact, so regardless for any convex body, cylinder or not, that specific local version of Log-Brunn-Minkowski conjecture, we do know when the function is like the scalar product with, it's like support function of an interval.
Okay, so that was already.
No, it was not known before. No, it was not known before. Now it's not. That was kind of the aim. No. I mean, this was our goal. We were like, okay, can we prove it for this one function? And the point is, for that one function, the second mixed volume actually is 0, right? Because it's like a second mixed volume with an interval. When you end an interval, it's a linear function. If you take second derivative of a linear function, you get 0. So, yeah. But for other functions, we don't know. The goal is to show it for all function, either to show it for all semi-norms together, these two complicated things, which is very tight and we don't quite know how, or to show it for all functions, but yeah, and again with the other part, with the second derivative part, but yeah, we don't quite know what to do with it.
Okay, thank you very much. Are there any other questions or remarks? If not, let's thank Galyna again, and
Thanks.
we'll see you all again next Monday. Thank you very much for attending.
Thanks.